Okay, so hello everyone. Thank you very much for the introduction and for the invitation to speak here. And let me remind you that this talk will have a surprise at around in 25 minutes, which is the fire alarm. So let's try to not get very scared when it happens. It will be some seconds and then I'll continue because probably I will not be done. So yeah. So the aim of the talk is to present some joint work with Léa Benesch, Henri Darmon, and Leonard German that aims to give a new proof to the Gross Kohnen Zagier theorem for the case of Shimura curves using the theory of p-adic uniformization. So let's begin with an outline. And for that, we take X a Shimura curve over Q and recall that this curve is equipped with a collection of special points called Higner points that happen to encode a lot of interesting arithmetic information. And the Gross Kohnen Zagier theorem states that certain classes made of Higner divisors appear as the coefficients of a modular form of weight 3/2 valid on the Jacobian of the Shimura curve. And the aim for today is to explain this theorem and a p-adic approach to prove it. And for that, we'll follow the next steps. So first, we'll give a basic example of a theta series. And the reason we will do that is because the Gross Kohnen Zagier theorem can be thought as a geometric generalization of the notion of a theta series. So then I will introduce which are the geometric ingredients that will play a role, which are the same that appeared in the talk by Mike. So these are Shimura curves and Higner points that we'll describe also via the theory of p-adic uniformization. And at that point, we'll be ready to state the Gross Kohnen Zagier theorem. And we'll conclude with some ideas of the proof, which use the theory of p-adic families of theta series. So if we had to summarize the proof in a couple of sentences, we would say that the key is that the classes of Higner points viewed in the CP points of the Jacobian can be described using Fourier coefficients of derivatives of p-adic families of theta series. So then the modularity statement involving the Gross Kohnen Zagier generating series that can look maybe rather mysterious follows from a simpler modularity statement involving theta series. So let's begin with a basic example of theta series that we will motivate with a Fermat-Christmas theorem. So it says that the prime P can be written as a sum of two squares, even only if P is 2 or P is congruent to 1 mod 4. And the first proof of this theorem was due to Euler, but today we are more interested in an approach in the lines of the work of Jacobi. So Jacobi studied these quantities, Rn, which is the number of pairs x, y, and z square, such that n is equal to x squared plus y squared. And he studied these quantities by putting them into a generating series and study properties of the generating series. And note that if we understand Rp well, we will be able to prove the theorem. And the key property that this generating series satisfies is that thanks to Poisson's summation formula, if we call theta of Q the generating series made of the Rns, then note that we can write as the sum of vectors in the lattice z square of Q raised to the length of that vector. This is the Q expansion of a modular form of weight 1, level gamma naught of 4, and non-trivial character, phi 4. So this statement is already nice by itself, the fact that we can construct a modular form using information about the lattice in this way. But now the idea is to try to use properties of modular forms to deduce things about the Rms. So the key property is that this space of modular forms is one-dimensional, and the theory of Eisenstein series provides an explicit element in there, which is this E of Q, such that its Fourier coefficients Q to the n is the sum over the divisors of n of the value of the character at d. And now we have two elements in a one-dimensional space. So they have to be multiples one to another one. And by comparing the constant terms, we see that they are actually equal, leading to an explicit formula for the Rns. And in this way, we can prove Fermat-Christmas theorem. And as I said, the aim for today is to study geometric generalizations of this theta series, of this construction. And we'll also say some words about this second part, meaning when you know that something is a modular form, we can deduce things about their coefficients because they need to satisfy a lot of interesting relations. So let's now introduce the geometric ingredients for this generalization. Here I'll be slightly faster because almost everything has been said by Mike. So we want to describe Shimura curves, but we'll directly describe them via its p-adic uniformization. So for that, we need to take a definite quaternion algebra over Q of discriminant coprime to P. We take R an Eisler Z1 over P order and a square free level, and let gamma be the units of norm 1 in this order. So this gamma should play the role of the usual gamma naught of n that we use to complex uniformize modular curves, for example. And in this case, we will make this group act on the p-adic upper half plane, that it's a rigid analytic space. And the way we do it is we choose a splitting of the quaternion. We choose an isomorphism of B tensor QP with the algebra of matrices with QP coefficients. And using this isomorphism, we can view the group gamma inside SL2QP, and therefore make it act by Moebius transformations. And this action is discrete, and it follows that HP mod gamma inherits a natural structure of rigid analytic space. And therefore, we have a nice theory of analytic functions and of meromorphic functions. And the key theorem that was already mentioned is that there exists an algebraic curve defined over Q, which is in fact a Shimura curve, such that if we take the CP points of this curve, this is isomorphic to HP mod gamma as rigid analytic spaces. So for the aim of today's talk, you can just think that the Shimura curve is HP modulo gamma, because we will not need more information than its CP points. And now what I'm going to do is describe you this collection of special points called Higner points via the p-adic uniformization. And this is what will lead to our analog of the RNs. And it is useful to write things in terms of this quadratic space V made of the trace zero elements in the quaternion algebra, where the pairing is induced by the reduced norm. And this is a quadratic space of signature 3,0, because our quaternion algebra was definite. And our Higner points will be indexed essentially by vectors in this quadratic space, such that they have length an integer, which is automatically positive, and satisfying the Higner condition, which is that the square root of minus n is not in QP. And when we have an element that has trace 0 and norm n, this element inside the quaternion algebra behaves exactly like a square root of minus n. So in other words, it induces an embedding of this quadratic imaginary field inside B. And now we can do something very similar to what we did with gamma. So we can use this embedding to view this Q. You can use the splitting of the quaternion algebra to view these units of the quadratic imaginary field inside GL2QP and make it act on HP by Moebius transformations. And one could study this action and study the fixed points of that action. And we get that there are exactly 2 fixed points in HP that I'm denoting by zip CV and zip CV bar. So the idea is that if you want to find the fixed points via Moebius transformation, you need to solve a quadratic equation. And this condition that the square root of minus n is not in QP ensures that the solutions of the quadratic equation are really in the p-adic upper half plane, meaning that they are not in P1 QP. And for us, a Higner point is simply a point in HP mod gamma that is of the form zip psi v or zip CV bar for some v as above. These are the points that now we describe using this p-adic uniformization, but happen to have a lot of interesting information. And now we're ready to give what will be our geometric analog of the RNs, which will be essentially an average of these Higner points. So this will be this delta. It will be a class of a divisor, delta n, that is a divisor in the Shimura curve HP mod gamma. And it's defined as a sum over vectors of length n, but we take the sum over vectors in this Z1 over P lattice made of the trace zero elements of our maximal order, modulo the conjugation action by gamma. And for each of these vectors, we put the 2 Higner points attached to M. So you can start seeing that this is quite analogous to the Rn, as the Rn was a sum over the lattice Z square of vectors that had length n. The only difference is that the thing we were adding was the function 1 in that case to count them. While here now we're putting this information. So the first observation then is that if we take the degree, it's very tempting to say that the generating series that I'm calling degree of G, made of the degrees of these divisors, will be a modular form of weight 3/2. And this is indeed what happens. The idea for that is that one can really relate this degree of G to some combination of theta series attached to V, because one can replace this sum over this Z1 over P lattice modulo gamma to a sum over a finite number of Z lattices. And that's how one relates these two theta series and proves the modularity. So this, we couldn't say maybe that it's a generalization of a theta series, but maybe it's a geometric interpretation of certain sums of theta series as degrees of divisors. But the observation of Gross Kohnen and Zagier at that time was that we can do a lot more things with the divisors than calculating their degrees. So what they did is they computed height pairings between difference of these Higner divisors and managed to obtain the result in terms of Fourier coefficients of also modular forms of weight 3/2. And this is what led them to the what we call now the Gross Kohnen Zagier theorem, that in the case of Shimura curves, it was actually proved by Borchert and Yuan Zhang first, which says that if we make a generating series, but where the coefficients are classes of these Higner divisors, so this is a generating series with coefficients in the Picard group, this is a modular form of weight 3/2 taking values in this group, Picard group. And what this means is that if you take any functional from the Picard group to Q, and you apply this functional to each of the coefficients, then you will get a honest Q expansions where the coefficients are numbers, and the claim is that this is the Q expansion of a modular form of weight 3/2. And you can see that as an example of functional, we can apply the degree map. So this proposition above gives an example of this functional, of a functional. But the observation of Gross Kohnen and Zagier is that we can apply a lot more functionals. The functionals they studied was take the height pairing with a fixed Higner class. So now I'm going to do a small reduction of the theorem where the divisors that appear all have degree 0. And then I'll briefly mention some applications of this theorem. So let's take L some prime and consider the Hecke operator TL minus L plus 1 the identity. So if the prime L doesn't divide this product I wrote here, the Hecke operator TL has degree L plus 1. So then automatically, if I apply T to any divisor, I transform it to a divisor of degree 0. And the observation is that thanks to the fact that we already know the modularity of the degree of G, to prove the full Gross Kohnen Zagier theorem, it's enough to prove that the generating series GT obtained by applying T to each of our divisors. So now it's a generating series valid in the Jacobian. This is a modular form of weight 3/2. And the reason for that is because to prove that we have a modular form, we have to prove that for every functional of the Picard group, if we apply it to our coefficients, we get a modular form. But we can write every functional as a linear combination of the degree map and the functional that factors through T. And we already know that if we apply the degree map, we get a modular form. So at this point, this is the theorem that we will try to prove in a moment. But before that, just in the same way as we did with the example of the theta series, I would like to say some nice consequence of this theorem. So not only it's nice because it's a generalization of theta series, but now the modularity of this implies that these Higner divisors need to satisfy a lot of conditions for being a modular form. So let's see some of the applications. So I wrote here in progress because the point 1 is actually very well known, but we're trying to deduce it from our proof itself. So this thing is still a bit in progress. And the first one is the one that motivated the most Gross Kohnen and Zagier to work on this. So let's take as functional the projection from the Jacobian to an elliptic curve. And we can apply this functional to each of our coefficients. And my claim is that the fact that the generating series made of the projection of our Higner points to an elliptic curve is a modular form, so the Gross Kohnen Zagier theorem, together with some extra work, implies that the rank of the group spanned by these Higner points is smaller or equal than 1. And by the time of Gross Kohnen Zagier, this was quite important because by that time, just a bit before, Gross Zagier had proven the Gross Zagier formula that was saying that if an elliptic curve has an analytic rank 1, then we can produce a rational point using Higner points that are non-torsion. But then they were a bit afraid because this construction of Higner points works for a lot of different values of n. So one could be afraid that, oh, maybe all these Higner points are producing too many points, more than the ones predicted by the BSD conjecture. And this type of theory allows us to ensure that actually all these points are collinear. So they at least don't contradict the BSD conjecture. Of course, now there's slightly stronger methods due to Kolivagin to prove these results. But the next observation is also that this construction of Higner points that we made and the proof that we present is very based on p-adic methods. So then one could hope that this same thing works for types of points for which we have a very p-adic construction, but maybe we don't know that they are global points, such as star-Higner points, that in fact the version of the Gross Kohnen Zagier theorem was proven by Darmon and Wong. Or even one could expect a Gross Kohnen Zagier theorem for plectic points, this work of Cornea and German, and we're actually working on this. And in that case, we have no idea about the algebraicity, but it's maybe optimistic, but possible to expect that the Gross Kohnen Zagier theorem of this style could give us some hope about the bound of the span of these points, and therefore some more evidence towards they are the right thing to consider. Okay, so since I see that I have a bit of time, according to my plan, I'll also mention that this is very important also for some of the things that Mike mentioned in the style of this Borchardt theory. So this also tells you which combinations of Higner points will be principal, and we can expect to construct invariant functions with these divisors. And this is also used in the world of rigid cocycles. So at this point, I hope I motivated you enough to see the proof of this new p-adic proof of the theorem. And let me say that if not, in the end of the proof, there's also a theorem that is interesting on its own. So the proof of the theorem has two steps. One step is understanding very well the CP points of the Jacobian. Because if we understand this very well, we'll be able to understand very well its functionals, and we'll have a way to test the theorem. So we'll be able to say for every functional, if we apply the functional, we get the modular form. And this comes from something that it's called the p-adic Abel-Jacobi map, that is the sum of the functions that actually Mike introduced, even though I will not say it. So this is an explicit isomorphism between the Jacobian of HP mod gamma and the group of morphisms from gamma to CP star modulo some Z lattice. That I will not say explicitly, but let's write this isomorphism as saying that the class of a divisor delta maps to the class of a morphism J delta. And the summary of how this J delta is constructed from delta is this one. So we have our delta. You choose a lift to a divisor on HP. Now, using the functions that Mike introduced, this type of infinite products, we construct a function on HP that has divisor precisely all the gamma translates of my lift. And now I check if this function that we constructed on HP is gamma equivariant. And how do we check this? We check it by computing an automorphic factor, JD, that will be a morphism from gamma to CP star. The idea is that if the automorphic factor is trivial, it implies that our function is gamma equivariant and descends to a function on HP mod gamma. And therefore, this implies that, and it has divisor precisely delta, implying that my divisor was principal. So this is a bit the idea about why this morphism provides the isomorphism I wrote above. So now we have this isomorphism between the Jacobian and this group of morphisms. So we can phrase the Gross Kohnen Zagier theorem in terms of these automorphic factors. So the conclusion is that to prove the Gross Kohnen Zagier theorem, it's enough to prove that the generating series that I'm denoting by GT plus made of the automorphic factors, now it's a modular form. And it should be a modular form taking values in this group of morphisms from gamma to CP star modulo lattice, but I skipped some technical steps. And I can tell you that one can justify that we can forget about this lattice and replace CP star by ZP star, just because our divisors are defined over Q essentially, because we're taking an average. So we have reduced the proof of the Gross Kohnen Zagier theorem to prove that this generating series, it's a modular form valid in the group of morphisms from gamma to ZP star. And one thing we gained is that the function of this group is very easy to describe, because this group is a group of morphisms from gamma to ZP star. So the functionals are essentially, you take a morphism, you evaluate it at a fixed gamma, and you take the p-adic logarithm to make things additive. So the functionals are indexed by elements in gamma. We have a very explicit classification of all of them. And the second thing we gain is that these automorphic factors attached to Higner points can be computed explicitly. And for this, we use the functions that Mike mentioned. So it's possible to produce functions in HP with prescribed divisors, because this because HP looks a lot like P1CP, let's say it this way. So now the way the proof works is, let's choose a gamma, let's apply the functional evaluation at gamma and take the p-adic logarithm. Let's compute this explicitly. And this is a tough computation, but nice. And let's try to compare this to something that it's a modular form. And now, due to time reasons, we'll skip all the computations, and I'm going to give you the construction of the thing that we compare applying the functional gamma to this. That will be a modular form. And for that, we'll use p-adic families of theta series. So remember, this construction will depend on a given gamma, that is the thing that indexes our functional. And the first observation is that the conjugation action of gamma on V tensor QP diagonalizes. And let me write here the eigen. Yeah, that's the moment. It was not scary. So let's resume. So the action of gamma on V tensor QP diagonalizes, and we can take the eigenvectors, which let me denote them by W plus, E, and W minus. And I claim that two of these eigenvectors, W plus and W minus, have length 0. So this can sound reasonable to you, maybe if you remember that V tensor QP correspond to matrices of trace 0. And so you have to think that these vectors are something like the E is the diagonal AI minus 1, and the W plus and W minus are something like a 1 in one corner and the 1 in the other one. So they have length 0. This is just some conjugation of this fact. And my goal is to use this data to construct theta series. So on one hand, we can take L to be the lattice generated by these three eigenvectors. And I consider a ZP lattice. And I scale the eigenvector such that this is unimodular. So this gives us a ZP lattice inside V tensor QP. On the other hand, recall that we had this maximal Z1 over P order. And if I take the trace 0 of this gives me a Z1 over P lattice in V. So I have a ZP lattice and a Z1 over P lattice. If I combine these two things, this will give me a Z lattice, and I will be in conditions of constructing theta series. And we will not only construct one, but we'll construct a collection of theta series for several weights. And this is the formula. I know it looks scary, but it's actually simpler than what it looks. So I'm going to try to explain it. So we construct theta series that will depend on K. K will be the weight. They will have weight 3½ plus K. And they depend on this data of a lattice L we choose, and either plus or minus according to the eigenvector we choose. And the first thing is a sum over all V's in V, Q raised to the length of V. So this looks a bit like a theta series. The only thing is that usually theta series need to have sums over Z lattices. So this is why these first two terms, which are these two functions, will account for this. So the first thing is a combination of characteristic functions of a Z1 over P lattice. This characteristic function of R trace 0 may be heated by the Hecke operator T. And the second thing is a combination of characteristic functions of ZP lattices. So the V is in L, that was our ZP lattice, and we add this condition that V pairs to a p-adic unit with the vector W plus, for example. So now this sum here corresponds to summing over a lattice. So if I do this, and I just do Q raised to the length of V, I get a modular form of weight 3½ using the classical theory of theta series. But there's also a classical theory of weighted theta series that tells you that if in this sum you add the pairing of V with a vector of length 0 raised to the K, this is what it's called the harmonic polynomial on V, and this gives you a modular form of weight 3½ plus K, the degree of this polynomial. So we have produced a collection of modular forms for several different Ks. And the nice thing is that these modular forms actually satisfy nice congruence relations on their Fourier coefficients. This is simply because of Fermat's little theorem. If we take K1 and K2, which are highly congruent modulo P minus, or congruent modulo P minus 1 times P to the N, since these numbers are p-adic units, just because we impose it, the Fourier coefficients, these numbers will be congruent modulo P to the N, because they are p-adic units. So in this way, we have actually produced a collection of modular forms that satisfy very nice congruences. If K and K prime are congruent, the modular forms of weight 3½ plus K and 3½ plus K prime will be congruent. So what we do with this is we choose a suitable combination of theta series of this style, where we vary the lattice L, because it can be scaled in several ways to make it unimodular. And we also vary the pluses and the minus. And this combination of theta series happens to satisfy these properties. The first one is that at weight 0, at the specialization at k equals 0, which is at weight 3/2, it vanishes. And you have to think that this looks reasonable because when k is 0, there's not much difference between the W plus and the W minus, as here we don't have anything. So if you take a suitable combination, everything vanishes. And when we have something that vanishes at k equals 0, we take the derivative. So if you take the derivative of this family with respect to k, so this will make some logarithms appear, and we evaluate at k equals to 0, what we do is we check that if we apply the ordinary projector, which is the same thing that Mike explained, we can compare this to the Gross Kohnen Zagier generating series after applying the functional evaluation at gamma and taking the p-adic logarithm. But now the theory of p-adic families of modular forms tells us that this right-hand side is a modular form. And therefore, so is the left-hand side. And this gives the proof of the Gross Kohnen Zagier theorem. So this is it. Thank you very much.
All right, thank you very much. Are there any questions?